Hello CIO class, and welcome to another installment of Chemical Engineering. This is Piping System Design. In this lecture we will focus on the considerations we make when designing piping, specifying fluid movers as well as flow rates. Now, for any chemical process, throughput is by far the most important factor to consider. The theory of constraints tells us that the product that spends the least amount of time in the process is also the most profitable product. So when your boss hampers on that one product of theirs that makes it out of the process after 6 months, takes 6 months to produce it, tell them that their most profitable product is in fact the other product that zooms through the process within 6 hours instead. However, processes also need to be designed safely and without unnecessary failures. As such, a suitable velocity needs to be selected so that it is not too slow or not too fast, like Goldilocks's porridge. Now, also check the velocities before finalizing the final specifications for the process to make sure you meet the design specifications at the end of the day. This goes hand in hand with the economic evaluation that is completed for the process, but this is something that will be covered in a later module during your final year of chemical engineering. Now, for chemical processes, a general rule of thumb is generally followed. These rules of thumb are called heuristics, and this heuristic applies to velocities, where namely fluids that are liquids should take on a velocity of between 1 meter per second and 5 meter per second. And for gases and vapors, of course this will be slightly higher at 5 meters per second up to 100 meters per second, but this is generally determined on the fluid. So for more specific boundaries, you can check the appendix or the appendices at the back of the handbook, or you can also look online if you're working with a specific fluid that isn't in the handbook. And also remember to check for any detrimental occurrences like sonic flows, for instance, but also very, very sluggish flows. As mentioned before, low throughput is usually uneconomic, and so we try to avoid laminar flow as much as possible. And if the flow contains any suspended solids or is a slurry or is just not a very clean pure fluid, it is likely that sedimentation would occur, resulting in blocked pipes and also certain types of corrosions. It is also possible that precipitation could take place, or the formation of stagnant flows could also occur. Now, during my time in industry, this was a serious issue for one of our bleaching towers that I was working on at the time, where several thermocouples were reading lower than expected temperatures due to stagnation, where the flow had stopped because the flow through the it's like a massive reactor, 6 meter in diameter. The flow was just not flowing. It was flowing laminar flow in the center and not flowing at all on the side. So this resulted in there being a much higher temperature inside the reactor rather than it having good mixing. Stagnation caused pockets of cold pulp to be measured, and so the process controllers thought that the reactor was operating below 80 degrees when in fact they had already heated the output to 95 degrees, which is unsafe. Alright, so on the other hand, high flow rates are also dangerous in that they may damage piping as well as equipment. So such flows also cause erosions, they cause vibrations to pipes and equipment, and can usually result in mechanical failures or even static charges, which can be a source of ignition, especially if you're working in a flammable environment. You definitely don't want this. Think of when you rub a balloon on your hair. It's kind of the same thing that occurs with pipes. Static charges can occur if pipes aren't properly earthed, for example. Now, the choice of wall thickness is also obviously very important. If your walls are too thick, the capital cost will be uneconomically high, and you could have gone perhaps for a smaller diameter pipe instead. But too thin walls can also result in stresses and failures, such as burst pipes, ruptured pipes, etc. So it is therefore very critical that an economic pipe diameter is selected for the optimal wall thickness based on the operation temperatures and pressures, of course. You do find when you're selecting a pipe diameter, the suppliers of the pipes give you some correlation that you can use to determine the maximum yield stresses for those pipes at certain elevated pressures, and so they can tell you what are the maximum pressures that you can operate at under certain temperatures of operation. Now, the stresses placed on the walls of the pipes originates firstly from the static pressure of the fluid. So this isn't the dynamic pressure that is induced when the fluid is flowing. This is more the static pressure due to the differences of the internal pressures versus the atmospheric pressure, and this results in tangential stresses. So think about what happens when you suffer from high blood pressure. This sort of pressure that we're talking about is similar to that. Now, the flow as well, due to the dynamic pressure, can cause what is known as tensile stresses. So we're talking about that rho v squared over 2. That is the dynamic pressure, and that is used in the Darcy-Weisbach equation. So as the fluid runs past the wall, it can pull the pipe because of the friction, okay, and it can stretch the pipe, and this is known as a tangential or tensile stress gets induced. So obviously you can pull the pipe right apart and cause the pipe to burst. A third type of occurrence is obviously when you're dealing with corrosive materials. Corrosive fluids occur obviously because of their inherent properties. They can be acids or bases. They can be certain types of organic fluids where, let's say, you're working with a plastic pipe, and the plastic pipe can become dissolved in that fluid that you're working with. Corrosion can take place if an incorrect material of pipe is matched with the fluid in question. But remember to factor in contaminants that can also be present within the primary fluid as well. Any contaminants in small quantities, and just don't assume that corrosion won't be an issue. Water can be quite dirty. It's only very special water that is cleaned very well, that might not cause such issues. Usually when you have a very concentrated acid like sulfuric acid, it won't be as corrosive as a dilute acid towards stainless steel, for instance. So you must consider the concentrations and whether there are any even trace elements or dissolved salts present in the solution that you're pumping around, because these can cause corrosion, believe it or not. So chemical processes will always surprise you with their non-idealistic existences, and so don't treat them ideally. Always treat them in a realistic way and assume the worst rather than the best. Now, another source of concern is something called pulsating flow. Okay, so it is how the fluid movers themselves induce vibrations in the fluid that may elevate or depress pressures. So we're not just talking about high pressure but also low pressure, because this can form implosions of equipment. But also velocities, of course, and this happens in such a way that the integrity of the pipeline and equipment is tested to the point of failure. So the following graph shows you a realistic case scenario that was being measured, where a pipeline eventually ruptured due to a continuous pulsation in flow caused by a fluid mover. The range of transient pressure, the unsteady change of pressure, varies within a 4-bar range, which is quite substantial. Okay, this year in the CPJ module, I found that a lot of students were, um, allowing for this sort of variation of 4-bar, and I penalized them for this. This is just unacceptable, to just assume this. So this is, considered to be quite a considerable variance, and at times we often don't take this into account. It's very important that you take this into account and try to control for it. There are things that you can do to dampen out these effects, of course, but also just design the pipe that it can withstand the highest foreseen pressure that is induced by the pump. So the results may be disastrous if you don't, and you must be aware of these types of hidden dangers. Right, another scenario that can occur and will probably take place is a failure of a pump. Lo and behold, when you are in industry, there shall be a power failure, and pumps and valves, etc., will go offline. Okay, so do not assume that this will never occur. It will, and you have to deal with it. Now, a control valve can also induce, such variances, and what can happen is when the failure occurs, if there's a sudden loss in power, for instance, a pump could stop suddenly, a valve could close suddenly, creating what is known as water hammer. So you can try this at home. Just do it when your parents aren't looking. Open a tap completely, and then try to close the tap as fast as possible. Slam that tap shut. And if you are able to locate the upstream pipeline, or even the downstream one as well, watch what happens to it. Usually the pipe will vibrate so violently that it will make a strong noise, a hammer, and it will hammer itself back and forth. And if this occurs too many times, the pipeline will eventually rupture. So it usually goes ka ka ka. Alright, another way that water hammer can occur, other than a pump going off, another way it will occur, is if a valve suddenly loses power, or a signal is lost, or whatever the reason, and it fails shut. Now, at times we do want such valves to fail in the closed position rather than the open position, so as to prevent a buildup of possible harmful chemicals and prevent any spills on site. So some valves need to fail open, some valves need to fail shut. But this will also stop flow suddenly when the valve decides to all of a sudden shut closed within a second. And this will result in water hammer, and so we need to take water hammer into account when we are designing our pipelines. Now, water hammer is quite a difficult thing to model because of its discontinuous nature at times, because of the shock wave that it causes. However, there are fortunately some design equations that we can use to factor in such occurrences. The momentary pressure increases as a result of the water hammer and is described by the following equation above, where A is the linear velocity of the pressure shock wave given by the relation shown here, so you can calculate this. The values of K represent the liquid compressibility modulus, which is available in literature, while the variable E represents the modulus with respect to the pipe, which is of course also available to you. Now, how this equation is incorporated into your energy balance is simply by adding it to the energy balance. But firstly, we need to obtain the pressure allowance for a specific pipe material in question, specifically for water hammer. So for example, shown here are typical values that apply to cast iron pipes. Okay, while other similar allowances can be found for stainless steel, for example, copper tubing, and these pressure allowances are then just incorporated into the mechanical energy balance calculations as an additional term. Okay, now in the case of ductile materials, the minimum allowable wall thickness is typically calculated using the following equation. The corrosion term is always factored in, as there will always be some sort of corrosion that will have to be dealt with or planned for during the lifespan of the plant. Okay, so I mean this can be 20 years, 50 years. This value typically contributes the most towards the wall thickness calculation. It can be as large as 4 millimeter. It all depends on the operation. Pipes are often specified by a schedule number, which you would have seen previously, which is based on the thin cylinder formula used to define pipes typically, and separately from high pressure pipes. So high pressure pipes are generally used for steam lines, which are considered as thick cylinders, or else if you have a very high pressure reaction that you are doing in a reactor, then you would use what is known as thick cylinders. Cylinders are just referring to the fact that the pipe geometry is a cylinder. Schedule 40 pipes are generally used. They are the most commonly used all-purpose pipes in industry. Remember that the gauge pressure must be used here. Okay, since this is the pressure that the pipe will of course be experiencing, and not the absolute pressure. Also remember to check the units that are being used when you obtain values for the allowable stress, S, and the joint quality factor. These are obtained in peris. Okay, so just make sure that the units do work out and that you do end up with the correct units, usually in millimeters. Okay. Now once you know what the thickness of the pipe you require is, you can go on to selecting a pipe diameter, obviously, because you can determine a nominal diameter, but obviously you're going to have to think about the type of flow that you want to induce. Now both corrosion and scaling are major occurrences that are considered when determining the minimum wall thicknesses, and as I've said before, they make up the bulk of the calculation. And there are more heuristics that are applied here as well. So firstly, always remember to read the manuals provided to you by the manufacturers. It goes without saying that you did not know because you did not read. The choice is usually based more on experience. An experienced engineer typically knows how a material will react to the current plant that he is working on. For instance, when I was first designing my aquaponics system, I used the advice from an apparent expert in the field, only to find that they were completely wrong. And after much expense and more hard work, I had to rebuild and modify everything again. So I really do wish that I had applied the design criteria in the first place, and didn't trust in the information that I was receiving from these non-experts. So nonetheless, when working with steel pipe products, for example, it is best to select corrosion factors of between 2 and 4 millimeter, and in most cases you should at least plan for 1 millimeter at least, and this is bare minimum, but this is really playing with fire. Once you get into design, one really good source of information for you for specifically for design engineer is going to be Coulson and Richardson's volumes, and specifically volume 6, which is shown here. But you can also make good use of Perry's too, if you can't obtain a copy of this material. I think it's out of print now. I've got a really old version of this. I've got the 2nd edition, and I think there's the 5th or 6th edition out already. So next year, when you are, doing the designs for CPJ, you will also be required to consider the mechanical design of vessels and columns, distillation columns, etc. And the design of vessels must not only take into account the process conditions, the fluid pressures, temperatures, etc., but also the need for the vessel itself to support its own weight as well. The following heuristics are used to determine the minimum wall thickness for vessels, excluding the additional constraints that are then going to be imposed by the operating conditions of the fluids themselves. Pay attention. I often see students take shortcuts here and just don't pay attention to proper design, and this is where they often lose confidence and marks from the marker. Additional sources of information can be found in the pages of Coulson and Richardson's as shown here. Alright, so best you obtain a copy, or else use the library resources that are available to you to obtain an electronic version of Coulson and Richardson. Now at times the process layout lends itself quite well to inducing flows without the need of fluid movers, and this generally occurs when there is sufficient elevation available to you, such as the endpoint pressures. Maybe P1 is quite high under a lot of pressure, and perhaps you also have a good elevation. Okay, so endpoint pressures usually support normal flow in the direction that is of choice, together with the elevation. Right. The sum of these two pressure differences should always be quite negative, okay, negative and large large enough such that an economic flow rate can be achieved and maintained. The cost of such designs should always be better than the alternative case of using a smaller pipe diameter together with a fluid mover, since the fluid mover can make use of smaller pipe diameters and therefore cheaper pipe diameters, okay, and achieve the desired flow rate in the end. So one should always check this. Usually the following minimum requirements should be met. You should try and achieve these flow rates without using a fluid mover, and it is likely that if you achieve such flow rates, that such a system would more or less be economic rather than adopting a fluid mover instead. Now, speaking of fluid movers, let's discuss an important occurrence called cavitation. Cavitation is reminiscent of vaporization. Okay, it is more or less the same thing, where a liquid that is close to its bubble point can vaporize within the fluid mover itself, or even in the suction pipe just before the fluid mover. Cavitation causes much erosion to the mechanics of the pumps and as well as the pipes, and mechanical failure in fluid movers can be induced due to the sudden changes of the fluid properties, such as density. So you can imagine little beads of vapor going past and then popping next to the impellers, and when they do this, they cause almost like little jets that start to eat away like a dentist at the impellers. So a microjet that forms is not a good thing, and eventually you'll end up with no impellers and you won't be able to push the fluid through the pipeline at all. The cause of this is due to the suction that is created within the pipe before the delivery line of the fluid into the new section of pipe. So firstly, a loss in pressure will obviously occur as the fluid enters the pump due to the entrance, okay, the pipe exit, the entrance of the pump. And this will also be accompanied by the usual frictional losses that will occur at the wall. As the fluid interacts with the impellers, of course, it undergoes a very strong reduction in pressure. Okay, so there's usually a vacuum that's created before it leaves the impeller housing, where the pressure is increased much higher than what was behind in the suction line. Okay, in the upstream pressure. It is at this very low pressure drop condition where cavitation might occur if the liquid is close enough to its bubble point, or even if the pump is powerful enough to induce such low pressure drops that the pump itself induces cavitation irrespectively. Okay, now cavitation will not only damage the fluid movers, but it will also decrease the flow rate for the section of pipeline, obviously because you're now working with gases and vapors, right? So they have more compressibility, and so the pump is just compressing and decompressing and compressing, etc. And a lot of that energy is now not being transferred into kinetic energy. Now, if the fluid is at its bubble point, then it should not be allowed to decrease the pressure head lower than 3% of the normal expected delivery pressures that you are designing for. Another type of cavitation that can occur for fluids that are not necessarily close to their bubble points is when the fluid contains a significant amount of dissolved gases such as nitrogen or oxygen. So when you are at home and you see that there's this white milkiness in the water, it's usually because they were doing changeovers with the water pipes, and normally they drain the water pipes. There's a lot of air that gets in. When they close the pipes again and they open up the water pressure, that high pressure pushes the gas into the water, and obviously it's now at 9 bar or 10 bar until it comes out of your tap at home. And once it drops in that in atmospheric pressure, the pressure drops to atmospheric pressure, you have all these dissolved gases, specifically nitrogen, forms very, very small bubbles, and these bubbles are seen as that white opaqueness in drinking water. Well, I won't call it drinking water. It's not safe to drink anymore. Okay. So the typical damage that occurs to pumps is by erosion of the impellers, as shown here. Without the impellers, obviously the fluid will not move. So next time you're in industry, go to the mechanical workshop and ask to see examples of where impellers were damaged like this, and so the mechanics will probably have a sample to show you what typically occurs. Okay, so be sure to educate yourself always when you are doing your vac work, etc. Now, before getting into the next study objectives, I do encourage you to go over this chapter yourselves in more detail in the handbook, as there is a lot of information that is actually presented that does not necessarily occur in the slides. Obviously, I can't read the entire handbook for you, so this is just a summary. Now, the next concept that we will be dealing with is known as the net positive suction head. You'll see that we are jumping back and forth between a lot of different study objectives here, and a lot of them are quite tricky to grasp at first, so please be sure to read these sections and don't just rely on these slides, because you can be confused if you just rely on the slides themselves. Now the net positive suction head is a very important concept, and it goes hand in hand with the prevention of cavitation in the design of piping systems. Now when a process is designed, it is inevitably going to contain a certain amount of pressure behind a suction line. Okay, so when you place a pump in a line, there's going to be some pressure that the fluid mover can be working with. Okay, and this obviously will affect how the fluid mover can be specified based on the upstream pressure that is obtained. Now firstly, the system itself contains a certain amount of available net positive suction head, and this amount needs to be matched to the requirements specified by the fluid mover itself. Certain pumps have a certain required available required net positive suction head. So each pump is designed by its own manufacturer, and the manufacturer usually specifies this for you. So if this requirement is not met, it is inevitable of a result that undesirable operation conditions such as cavitation will occur. Okay. Now the available net positive suction head is determined from the following energy balance, and it has units of meter typically instead of kilopascal, but obviously you can just convert that yourself back to kilopascal if you prefer working in those units. The reason why we use meter typically is because most pump curves that accompany pumps are graphed in meter rather than kilopascal, as this is better visualized when designing the heights of columns, vessels, etc. Alright. Now make sure that you understand that the end point pressure P1 and the differential pressure due to the elevation both typically increase the net positive suction head, unless of course the vessel is below the pressure, the pump location. Okay. But in generally losses in the net positive suction head can result from any friction in the pipeline, and also if the fluid is close to its bubble point. Obviously if it's close to its bubble point or is at its bubble point, then pumping it is definitely not a good idea. So in other words, the net positive suction head is determined by the difference between the absolute pressure of the system minus the vapor pressure or effective pressure of the liquid. And this is important, remember, because the vapor pressure is also taken as an absolute pressure, not a gauge pressure. Now if there are only dissolved gases in the liquid, then the vaporization pressure is usually the effective pressure, or it's taken as the effective pressure instead. If the liquid is close to its bubble point, however, then delta P effective equals the endpoint pressure P1, obviously. If you don't understand why, give it some thought or ask me at a later stage if you are unsure of why this should be the case. So what of the requirement for a net positive suction head? I have a required net positive suction head for a pump. This is usually taken as the total pressure at the suction flange that limits cavitation to about 3% minus the effective vapor pressure of the liquid at operating conditions. What this says is that you should not worry too much about this or trying to figure out this value because it is in fact usually dependent on how the pump has been designed and manufactured, and this information is typically supplied by the manufacturer. The manufacturer says this is the required net positive suction head that you should design with. Okay, but once the required net positive suction head is known, or if you have a available suction head, net positive suction head that you have designed for, then we can apply certain design criteria to make sure that no cavitation will take place for the plant design. So firstly, in general, we design the net positive suction head available to be greater than or equal to the required net positive suction head plus half a meter. And remember, available is what we calculate, and required is what the supplier of the pump will specify to us. Now, when working with other types of fluids like hydrocarbons, the available net positive suction head is 10% more than what is required, and in the case of aqueous solutions, 20% more than what is required. It goes without saying that when the required net positive suction head is very small for the pump, the available net positive suction head will also be very small. However, such pumps tend to be very expensive, of course, but they also will allow you to make use of much smaller pipe diameters, which will save you on operating costs as well as capital costs in the end. Now, there are always other ways in which we can ensure we have enough net positive suction head available to us, such as by keeping the line, the suction line, short, and also increasing the height of the upstream fluid if this is at all possible, and reducing the operation temperature as well if this is again possible for the process in question. Remember, you can't just go and decide to change temperatures and change heights of things, because this has real life implications where we actually have to go and construct a completely new height of column, or that we have to change the reaction kinetics or the conditions of the reaction when we fiddle around with pressures and temperatures. So it's not always possible to make these changes. So don't just willy-nilly assume that these changes can be done. You must respect the limitations of the process in question. Now, in the design of a suction line, we firstly determine the elevation prior to the placement of a pump. Okay, so the suction line side. Then we follow the usual design criteria to design the piping and use the information that is provided to us, such as the information in Appendix G1 and Appendix G2. Now, with the elevation and diameters known to us, we go on to calculate the available net positive suction head and then determine what requirement we have for the net positive suction head when choosing a pump. Okay, so hereafter we can decide on the pump that we require using the design specifications that is needed for the plant to operate sufficiently. Now, when designing pipelines, it is often important to ensure that the flow proceeds in the right direction. At times, it might happen that flow reverses when there is downtime, or there's a power failure, or the process simply goes offline. Check valves are generally used to ensure that the flow can only proceed in one direction, so there can't be any flow backwards into the system, and can typically be used for any type of fluid. It all depends on the cracking pressure and the operation of the check valve, how it has been designed. Now, what should be considered is the cracking pressure that is required by the valve, which is the minimum pressure that is needed before the valve opens itself up. So there's a certain static and dynamic pressure that will be required to crack the valve open and keep the valve open. The release pressure, the reseal pressure, is when the fluid flow rate reduces enough to a low enough velocity such that the valve can close again. And the back pressure, therefore, has to be low enough, or it shouldn't be too low and it shouldn't be too high as well. It needs to kind of be in a sweet spot in order for the check valve to operate correctly, because you can imagine the back pressure, which is in the delivery side of the check valve. If that pressure is too high, then the cracking pressure will increase for the valve, and maybe you don't have enough pressure being supplied by a pump, for example, or by the elevation. So you need to be sure that you choose the right check valve that matches the pressure that it has to be operated under. The check valve is designed usually independently, but its pressure drop is of course included in the pressure drop calculations when you determine the frictional pressure losses. So firstly, choose the size of valve that corresponds best to the line size. So if you have a 25 millimeter line, choose a 25 nominal millimeter valve, and then determine the pressure drop that is obtained, and then just check that this pressure drop is larger than the minimum pressure drop that is required for the safe operation of this valve. And if this is not the case, then you may require a smaller valve, and so just choose a valve that is smaller. So if you have a 25 millimeter line, then choose a 20 millimeter nominal diameter valve. Okay, how do we typically measure flow? Now this is another question. It all depends on the type of fluid, the geometry of pipe, as well as the rate of fluid being targeted, and also operating conditions, pressures, temperatures, corrosivity, hygiene, etc. Now there are many ways to measure flow, and it is up to you to orientate yourself with the various types of instruments. Now a flow meter can either measure mass or momentum, in other words velocity, or volumetric flow rates. Now considerations pertaining to the type of flow meter that is chosen is matched with the type of fluid material. So the fluid, what is the material that is being pumped around? What are the conditions, the operating conditions? What is the flow range that can be expected? If you have a too high a flow or a too low a flow, the flow meter might not work as required. What is the required accuracy? As well as what are the other types of concerns, like are there any environmental concerns such as hygiene? Are you working in a food factory, for example? Coriolis valves, flow meters, offer very good mass flow measurements, but they are really expensive, while differential flow meters correlate pressure drops instead with volumetric or velocity flow rates. Magnetic meters, I've also seen in industry, use a magnetic field to determine the flow rate, but these only work for certain types of fluids and have additional requirements for pipe layouts, for example. You can't have pipes running parallel to each other too closely, because the flow in the other pipe might interact with the flow meter, the magnetic flow meter in the pipe that you're trying to measure. Alright. There are also things like paddle wheel meters, there are thermal dispersion meters, turbine meters, ultrasonic meters, variable area meters, vortex meters, venturi meters, pitot tubes, and rotor meters. There are so many to choose from indeed, so best you read up about them and choose the specific ones that are required for your process. Now one of the simplest types which can be constructed even at home is called an orifice flow meter. If you only have a certain pipe diameter less than 50 meter, then this is probably not for you, because they can only be used accurately for lines with diameters that are larger or equal to 50 millimeter in diameter. Okay, and also where large pressure drops can be tolerated, the pressure drop is what is used here. So the pressure drop across an orifice plate generates a signal, and the signal can also then be used for flow control. So both flow measurement as well as flow control. An orifice plate is typically used for flow control as follows. It's just a plate, a very thin plate that is placed in between two flanges of a pipe section through which you have drilled a hole and just made the hole nice and square but cylindrical in shape. Then the two taps are placed in line. One tap is placed before and one tap is placed after the flange where the plate is located. And the tap locations are also quite specific. We'll get into the design of these now, but the pressure drop then can be measured across these tap positions. So the tap positions, what you do is you insert a pressure gauge inside a pressure sensor, and then the pressure can be digital, be sent off to a computer, and then the computer will do the calculation for you. The design equations for orifice plates are shown here, where HW refers to the local pressure drop between the two taps. Beta is the ratio of the orifice hole and the pipe diameters. So the orifice hole divided by the pipe diameter that you're using. And then C is known as the coefficient of discharge. Now the coefficient of discharge is in fact a function of beta depending on the Reynolds number that you are operating at, and it is also a function of the tap positions and then obviously the Reynolds number. The orifice diameter is selected in such a way that beta lies between a value of 0.25 and 0.75, where 0.7 is typically the most popular choice. And this is chosen so that you have enough pressure drop, but not too much that it will become detrimental to the operation of the system. Now, notice here on the left-hand graph that C is a very strong function of the Reynolds number for any Reynolds number that's lying below 30,000. So what this means is that orifice plates are much less suitable for flows that have low Reynolds numbers, or in other words, very low flow rates. And a calibration would often be needed in this case. So you can use orifice plates for low flow rates. However, for high flow rates, C takes on a more or less constant value for Reynolds numbers of greater than or equal to 30,000, as you can see. And the graph then kind of stops because you just more or less take a coefficient of determination of 0.2 thereabouts. Okay, the choice of orifice size is also important. This needs to be matched to the correct placement of the downstream tap location, and this is shown correlated here in the bottom right hand graph. Okay, now the following graph on the left is also used to correlate the coefficient of discharge with the downstream tap location, and all of these graphs are available to you in the handbook for your perusal. Specifically, what is shown here is the vena contractor, where you have the lowest pressure drop that will be induced, and obviously this is a good place to be measuring so that you can have a very sensitive measurement. Alright, so let's quickly discuss the design of orifice meters. And firstly, what we need to do is to look at the flow rate, and how we do this is we determine the Reynolds number. Now, if the Reynolds number is greater than 30,000, we can simply insert the pressure meters without requiring further calibration to measure the flow rate. So if your Reynolds number is 30,000.965287, then you should be happy. However, If the flow rate yields a Reynolds number that is less than 30,000, one way that you can get around this issue is to reduce the pipe diameter. Obviously it still needs to be greater than 50 millimeter at the specific location that you intend to insert an orifice plate, such that a high enough Reynolds number is achieved and you have no calibration required for the coefficient of discharge. Okay, but remember, as most flow meters are sensitive to flow, it is very important to choose your location correctly. So for example, if you have a downstream T that is very close to a flow meter, this can cause disturbances in the readings, and an erroneous flow measurement can result. And so you think the flow is one value, but in fact it is another value. Okay, and other considerations to keep in mind for designing good orifice type flow meters is to use a thin enough plate and place the pressure taps at opportune locations, such as at the place where a vena contractor occurs, where a good pressure drop will be obtained, as this will increase the sensitivity of the measurement. And lastly, we will treat orifice plates or orifice type flow meters as pieces of equipment, so they will be included in delta PEQ, or we will correlate them as such, okay, for the MEB, and include their pressure drop into the mechanical energy balance as such, using the following equation, which is at the back of the chapter. And with that, we end off this lecture. And just remember, be sure to do your tutorial questions, specifically for this part of the work, as if you don't get enough practice in, this part of the work can be very, very difficult. And with that, I say goodbye for now. See you next time.